We are now concentrating on chapter 10 under the title Classification of Operators over Hilbert Spaces. In module 1, we have discussed on adjoint operators of a bounded linear operator acting from a Hilbert space onto itself. Now, we are going to discuss module 2. Basically, module 2 is devoted on the introduction of self-adjoint operators with its basic properties. We shall also discuss on eigenvalues and eigenvectors of adjoint operators along with self-adjoint operators. We are now going to discuss module 2 of chapter 10. The title of module 2 is self-adjoint operators over Hilbert spaces and eigenvalues and eigenvectors. Let us take a definition. A member T belongs to BD LHH is called self-adjoint if T equal to T star, that is inner product Tx comma y equal to inner product x comma Ty for all x comma y belongs to H. Let us take a theorem. If T1 and T2 are two self-adjoint operators over H, then T1 plus T2 is self-adjoint. Number 2, if T1 is self-adjoint and alpha be any real scalar, then alpha T1 is self-adjoint. Number 3, for any member T belongs to BD LHH, T star T, comma T star and T plus T star are also self-adjoint. Number 4, if T1 and T2 are two self-adjoint operators, then T1 T2 is self-adjoint if and only if T1 T2 equal to T2 T1. Let us take the proof for the first part. Now, T1 plus T2 star equal to T1 star plus T2 star, which is equal to T1 plus T2. This implies that T1 plus T2 is self-adjoint. For the second part, alpha T1 star equal to alpha bar T1 star, which is equal to alpha bar T1, which is equal to alpha T1 because alpha is a real scalar. For the third part, star of T star T equal to T star into star of T star, which is equal to T star into T, and star of T star equal to star of T star into T star, which is equal to T double star T star, which is equal to T star. Also, star of T plus T star is equal to T star plus star of T star, which is equal to T star plus T double star, which is equal to T star plus T, which is equal to T plus T star. Finally, star of T1 T2 equal to T2 star T1 star, which is equal to T2 T1. So, star of T1 T2 equal to T1 T2 if and only if T1 T2 equal to T2 T1. Let us take another theorem. The class of all self-adjoint operators form a closed real subspace of collection of all bounded linear operators from H to H, and hence it is a Banach space where H be a complex Hilbert space. If capital theta and I denote the 0 operator and identity operator, we have null operator, comma identity operator belongs to BD LHH. Further, star of null operator is equal to null operator itself and star of identity operator equal to identity operator. Now, if T1 and T2 are self-adjoint operators with alpha and beta two real scalars, we have star of alpha T1 plus beta T2 equal to alpha bar T1 star plus beta bar T2 star is equal to alpha T1 star plus beta T2 star because alpha and beta are real scalars, which is equal to alpha T1 plus beta T2. Showing thereby alpha T1 plus beta T2 is also self-adjoint. Further, if Tn is a sequence of bounded linear operators from H to H and Tn are self-adjoint such that limit n tends to infinity Tn is equal to T in operator norm, that is norm of Tn minus T tends to 0 as n tends to infinity, then capital T is a bounded linear operator on H. Now, norm T minus T star less or equals to norm Tn minus T plus norm Tn minus Tn star plus norm Tn star minus T star, which is equal to norm T minus Tn plus norm Tn minus T star, which is equal to norm T minus Tn plus norm Tn minus T, which goes to 0 as n tends to infinity. Hence, T equal to T star. This shows that T is self-adjoint. So, class of all self-adjoint operators with identity operator and zero operator forms a closed subspace of BDLHH. As BDLHH is complete, class of all self-adjoint operators is complete with respect to operator norm, and hence it is a Banach space, that is, it is a subspace of BDLHH. Let us take another theorem. Let T be a bounded linear operator from a Hilbert space H to H, that is, T belongs to BDLHH, and it is such that for all x comma y belongs to capital H, inner product Tx comma y is equal to 0, then T equals to the 0 operator, and conversely. For the 0 operator theta, we always have inner product 0 operator x comma y is equal to inner product 0 vector comma y, which is equal to 0. Conversely, let for all x comma y belongs to capital H, inner product Tx comma y equal to 0. Let x belongs to capital H be fixed and consider inner product Tx comma y equal to 0 for all y belongs to capital H. That means Tx is equal to 0 vector in H. Now, let x be free, and we see that Tx equal to 0 vector for all x belongs to H, showing that T equal to 0 operator. In this connection, we note the following corollary. If T belongs to BDLHH such that inner product Tx comma x equal to 0 for all x belongs to H, then T is the 0 operator. The proof follows like this. If x comma y belongs to H and alpha comma beta are any two scalars, then we have 0 equal to inner product T alpha x plus beta y comma alpha x plus beta y equal to inner product T of alpha x plus T of beta y comma alpha x plus beta y, because T is linear, which is equal to inner product alpha Tx plus beta Ty comma alpha x plus beta y, which is equal to alpha alpha bar inner product Tx comma x plus alpha beta bar inner product Tx comma y plus beta alpha bar inner product Ty comma x plus beta beta bar inner product Ty comma y, which is equal to alpha beta bar inner product Tx comma y plus beta alpha bar inner product Ty comma x. Other terms are 0 by the given condition. Let us take alpha equal to 1 and beta equal to 1. We then have inner product Tx comma y plus inner product Ty comma x equal to 0. This is equation number 1. Again take alpha equal to I, beta equal to 1, we have I into inner product Tx comma y minus I into inner product Ty comma x, which is equal to 0. This implies that inner product Tx comma y minus inner product Ty comma x equal to 0. This is equation number 2. Adding equation number 1 and equation number 2, we have inner product Tx comma y equal to 0, and by previous theorem we see that capital T is the 0 operator. Let us take another theorem. Let T be a bounded linear operator from H to H, that is, T belongs to BDLHH, then T is self-adjoint if and only if inner product Tx comma x is real for all x belongs to capital H. The proof looks like this. Let T is self-adjoint, so T equal to T star. Now, conjugate of inner product Tx comma x equal to inner product x comma Tx, which is equal to inner product x comma T star x, which is equal to inner product Tx comma x, because T equal to T star. This shows that inner product Tx comma x is real. Again, let conjugate of inner product Tx comma x equal to inner product Tx comma x. So, inner product Tx comma x equal to conjugate of inner product Tx comma x, which is equal to conjugate of inner product x comma t star x, which is equal to inner product t star x comma x for all x belongs to capital H. This implies that inner product Tx comma x minus inner product T star x comma x is equal to 0. This implies that inner product Tx minus T star x comma x equal to 0, which implies that inner product T minus T star x comma x equal to 0. So, by previous corollary, we see that T minus T star is the 0 operator, that is T minus T star equal to null operator, which implies that T equal to T star, and this shows that T is self-adjoint. Let us take another theorem. Let capital H be a Hilbert space and let T be a bounded linear operator from H to H, that is T belongs to BD LHH, and it is such that T is self-adjoint. Then norm T equal to supremum of modulus of inner product Tx comma x, and supremum is taken over all such elements with norm of x equal to 1. The proof looks like this. Now, modulus of inner product Tx comma x is less or equals to norm Tx into norm x for all x belongs to H with norm x equal to 1, which is again less or equals to norm T into norm x square, which is equal to norm T because norm x equal to 1. Therefore, supremum of modulus of inner product Tx comma x and supremum is taken over all such elements x with norm x equal to 1 less or equals to T. Conversely, we show that norm T less or equals to supremum of modulus of inner product Tx comma x and supremum is taken over all elements with norm x equal to 1. Let capital K equal to supremum of modulus of inner product Tx comma x and supremum is taken over all such elements x with norm x equal to 1. We are to show that norm T less or equals to K. We now study the following cases. For case 1, Tx equal to 0 vector for all x belongs to H with norm x equal to 1. This implies that T equal to 0 operator on H. So, in this case we have finished it. For case 2, let Z belongs to capital H be any vector such that norm Z is equal to 1, but Tz not equal to 0. Put V equal to root over norm Tz into Z and W equal to 1 by root over norm Tz into Tz. Let Y1 equal to V plus W and Y2 equal to V minus W. Now, norm V square equal to norm Tz equal to norm W square. So, by routine calculation and using the fact that T is self-adjoint, we see that inner product T Y1 comma Y1 minus inner product T Y2 comma Y2, which is equal to inner product T V plus W comma V plus W minus inner product T V minus W comma V minus W, which is equal to 2 times inner product T V W plus inner product T W V, which is equal to 2 times inner product T Z comma T Z plus inner product T square Z comma Z, which is equal to 2 times inner product T Z comma T Z plus inner product T Z comma T Z, which is equal to 4 times norm T Z square. This is equation number 4. Let y belongs to capital H be such that y not equal to 0 vector. Put x equal to y by norm y. So, norm x equal to 1. Now, inner product T y comma y equal to inner product norm y into T x comma norm y into x, which is equal to norm y square inner product T x comma x. So, modulus of inner product T y comma y is equal to modulus of norm y square into inner product T x comma x, which is equal to norm y square into modulus of inner product T x comma x, which is less or equals to norm y square into supremum of modulus of inner product T x comma x, and supremum is taken over all such elements x with norm x equal to 1, which is again equals to norm y square into capital K. So, modulus of inner product T y1 comma y1 minus inner product T y2 comma y2 is less or equals to modulus inner product T y1 comma y1 plus modulus inner product T y2 comma y2, which is less or equals to K times norm y1 square plus norm y2 square, which is equal to 2 times k into norm v square plus norm w square, which is equal to 4k into norm tz. Thus, 4 into norm tz square less or equals to 4k into norm tz by equation number 4. So, 4 norm tz square less or equals to 4k norm tz. Hence, norm tz less or equals to k. So, supremum of norm tz and supremum is taken over all such elements z with norm z equal to 1 less or equals to capital K. Hence, norm t less or equals to k, which is equal to supremum of modulus of inner product Tx comma x and supremum over norm x equal to 1. So, by equation number 3 and 5 we get norm t equal to supremum of modulus of inner product Tx comma x, where supremum is taken over all such elements x with norm x equal to 1. Up to this, in module 2 of chapter 10 we have discussed on self-adjoint operators. We have also discussed on some basic properties of self-adjoint operators. Now we are going to discuss on eigenvalues and eigenvectors of adjoint operators and self-adjoint operators over a Hilbert space. We are now going to discuss on eigenvalues and eigenvectors of self-adjoint operators. For this, let us consider capital H be a complex Hilbert space and let T belongs to BD LHH, that is, T is a bounded linear operator from a Hilbert space H onto itself. Let us take a definition. A non-zero vector x belongs to capital H is said to be an eigenvector of T corresponding to a scalar lambda called eigenvalue of T if Tx equal to lambda x, or Tx minus lambda Ix equal to 0, where I being the identity operator on H. That means T minus lambda Ix equal to 0 vector. In this connection, let us take a theorem. Let T belongs to BD LHH such that T is self-adjoint, then all the eigenvalues of T are real. The second part, the eigenvectors corresponding to distinct eigenvalues are orthonormal. Let us take the proof one by one. We are going to discuss the proof of the first part. Let lambda be an eigenvalue of T and x be a corresponding eigenvector of T, then x not equal to 0 vector and Tx equal to lambda x. Since T is self-adjoint, we see that lambda times inner product x comma x equal to inner product lambda x comma x, which is equal to inner product Tx comma x, which is equal to x comma T star x, which is again equals to inner product x comma Tx, because T is self-adjoint and T equal to T star, which is equal to inner product x comma lambda x, which is again equals to lambda bar into inner product x comma x. So, lambda times inner product x comma x equal to lambda bar times inner product x comma x, that is lambda into norm x square equal to lambda bar norm x square, where inner product x comma x equal to norm x square greater than 0 as x is a non-zero vector. So, we see that lambda equal to lambda bar and hence lambda is real. For the proof of second part, let lambda and mu be two different eigenvalues of T and let x and y be two non-zero eigenvectors corresponding to eigenvalues lambda and mu respectively. So, we have Tx equal to lambda x and Ty equal to mu y. Since T is self-adjoint and eigenvalues are real, we have lambda times inner product x comma y equal to inner product lambda x comma y, which is equal to inner product Tx comma y, which is again equals to inner product x comma T star y, which is again equal to inner product x comma Ty, which is equal to inner product x comma mu y, that is mu into inner product x comma y. So, inner product x comma y equal to 0 since lambda not equal to mu. This shows that x is perpendicular to y. In this connection, let us take a theorem. Let T is a bounded linear operator from H to H be such that Tt star equal to T star T. If x is a non-zero eigenvector of t with eigenvalue lambda, then x is also an eigenvector of t star with eigenvalue lambda bar and vice versa. The proof looks like this. Consider the operator t minus lambda I in H, where I is the identity operator on H. Then t minus lambda I into t minus lambda star equal to t minus lambda I into t star minus lambda bar I, which is equal to t star minus lambda bar t minus lambda t star plus mod lambda square into I. Similarly, t minus lambda star into t minus lambda I equal to t star minus lambda bar I into t minus lambda I, which is equal to t star t minus lambda t star plus lambda bar t plus mod lambda square into I gives t star t equal to t star. Therefore, t minus lambda I into t minus lambda star equal to t minus lambda star into t minus lambda I. Put t minus lambda I equal to s. So, s star equal to s star s. Thus, for x belongs to capital H, s star x equal to s star sx, which implies that inner product s star x comma x equal to inner product s star sx comma x, which implies that inner product s star x comma s star x is equal to inner product sx comma star of s star x, which is equal to inner product sx comma s double star x, which is equal to inner product sx comma sx. This gives that norm s star x square equal to norm sx square, which implies that norm t star minus lambda bar I x square equal to norm t minus lambda I x square, which implies that norm t x minus lambda x square equal to t star x minus lambda bar x square. This shows that norm t x minus lambda x equal to norm t star x minus lambda bar x, and this implies that t x equal to lambda x if and only if t star x equal to lambda bar x. Let us take an example. Let capital L201 be the real Hilbert space of all square integrable functions over the closed interval 01 with inner product function defined by inner product x comma y is equal to integration 0 to 1 xt yt dt as x comma y belongs to L201. Show that t from L201 to L201 defined by tx equal to y belongs to L201, where yt equal to txt with 0 less or equals to t less or equals to 1 is a bounded linear operator which is self-adjoint having no eigenvalues. The solution looks like this. Let x1 comma x2 belongs to L201, then t x1 plus x2 equal to z, where zt equal to t x1 plus x2 t, which is equal to t x1 t plus t x2 t, which is equal to capital T x1 t plus capital T x2 t, which is equal to t x1 plus t x2 t for all t belongs to 0 1. So, t x1 plus x2 equal to t x1 plus t x2. This shows that t is additive. Similarly, for any real scalar alpha, t alpha x equal to alpha t x for all x belongs to L201. Thus, t is linear. Now, norm tx square equal to inner product tx comma tx is equal to integration 0 to 1 txt into txt dt, which is equal to integration 0 to 1 t square x square t less or equals to supremum of t square into integration 0 to 1 x square t dt, and supremum is taken over all t lying between 0 and 1, which is equal to 1 into norm x square. So, norm tx less or equals to norm x, implying that capital T is bounded. Thus, T belongs to BDL L201 comma L201. Now, inner product Tx comma y equal to integration 0 to 1 txt yt dt, which is equal to integration 0 to 1 small txt into yt dt. Again, inner product x comma ty equal to integration 0 to 1 xt into capital T yt dt, which is equal to integration 0 to 1 xt small t yt dt, which is equal to integration 0 to 1 txt into yt dt. So, inner product Tx comma y equal to inner product x comma ty for all x comma y belongs to H, implying that T is self-adjoint. Let x not equal to 0 vector be the eigenvector of T and the corresponding eigenvalue of T is lambda. Show that Tx equal to lambda x. So, Txt equal to lambda xt for all t belongs to closed interval 0 comma 1. This implies that small txt minus lambda xt equal to 0 for all t belongs to closed interval 0 1. This implies that small t minus lambda xt equal to 0 for all t belongs to 0 1, but x not equal to 0. So, t minus lambda equal to 0, which gives that t equal to lambda for all t belongs to closed interval 0 1, which is not the case. Hence, lambda is not eigenvalue of T. In this connection, let us take a theorem. Every bounded linear operator T belongs to BD-LHH can be expressed as T equal to capital A plus I into capital B, where capital A and capital B are two self-adjoint bounded linear operators on H, and this representation is unique, where H being a Hilbert space. The proof looks like this. Let us define capital A equal to T plus T star by 2 and capital B equal to T minus T star by 2I. By routine calculation, we see that A equal to A star and B equal to B star. Also, capital T equal to capital A plus I into capital B. If possible, let T equal to capital C plus I into D, where C and D are self-adjoint. So, T star equal to C minus ID, which gives T plus T star by 2 equal to C and T minus T star by 2 equal to D. So, capital A equal to capital C and capital B equal to capital D, showing that this representation is unique. In this module 2, we have learnt self-adjoint operators over a Hilbert space. Also, we have discussed some basic properties of self-adjoint operators. Also, we have learnt how to find out the eigenvalues and eigenvectors of self-adjoint operators over a Hilbert space. With this, we now come to an end of module 2 of chapter 10.